We will start out by looking at electromagnetic waves in free space or lossless dielectrics. This is a different approach than the one your book takes. Your book starts out looking at the most general case and treats the conditions of free space or lossless dielectrics as special conditions. The approach your book takes requires working with phasors, and things are very mathematically abstract. I think the approach we take will give a better mental representation of how Maxwell's equations lead to electromagnetic waves. If we are in free space or dielectric, there's no free charge, so the free charge density is equal to 0. If it's lossless, it means no currents flowing, there's no I squared R losses, so the current density is equal to 0. So in Maxwell's equations in point form, rho sub V is 0 and the free current density is 0. We want to state Maxwell's equations just in terms of the electric and magnetic field intensities. So for the electric flux density fields, we're going to substitute epsilon times E, and for the magnetic flux density fields, we're going to substitute mu times H. In Gauss's law, we can divide both sides by epsilon to get del dot E is equal to 0, and similarly our second equation becomes del dot H is equal to 0. So here's the form of Maxwell's equations in point form for free space or a lossless dielectric. If this was free space, mu and epsilon would just become mu sub 0 and epsilon sub 0. Let's take the curl of both sides of this equation, which will result in this equation here. For the curl of H, we will substitute epsilon times the partial of E with respect to time. So we'll have this equation here. Here is a vector identity for the curl of E. And the divergence of E is equal to 0, so this first term goes to 0. So the curl of E can be replaced with minus the Laplacian of the electric field intensity. So on the next page, I will write this term equal to this term. Here's the result we had from the previous page, and here I'm just rewriting it. You could go through a similar procedure and get an equation for the magnetic field intensity. These two equations, E and F, are called wave equations because their solutions are propagating waves. If we're working in Cartesian coordinates, then the Laplacian of the electric field intensity takes on this form. Since the electric field intensity is a vector, the electric field intensity has a component in the x, y, and z direction, so we'll have an equation like this for each one of the three components. So here's what the equation would look like for the x component, and the x component of the electric field intensity can depend on x, y, z, and time. We are going to look at the solution to this equation that only varies in the z direction, is constant in the x and y direction. We'll see this is what is referred to as a uniform plane wave. If you have a radiating antenna, the electromagnetic waves will be a spherical wavefront. Let's think about this in terms of dropping a pebble in a pond. So you can visualize those water waves leaving with these spherical wavefronts. The farther you get from where you drop the pebble, the less curvature the wavefronts have, and they approach what we refer to as a uniform plane wave, so it looks like planes of waves coming past the observer. So for large values of z, it will look like your wavefront only varies with z and doesn't vary with, say, x or y. Substituting this form of the electric field intensity up here, you see the partial with respect to y is 0 and the partial with respect to x is 0. So here is our wave equation for this uniform plane wave. Here is the simplest form for that uniform plane wave. To verify this is a solution, let's substitute in our wave equation here, and what we'll end up getting is the condition upon which this is a solution to our wave equation. I've made that substitution. Now we have to do these two differentiations. Taking the partial of the cosine with respect to z, we get minus the sine, and taking the partial with respect to z of the argument here, we get a minus beta. Taking the partial with respect to time here, we get a minus the sine, and differentiating with respect to time, the argument, we get an omega. So I factored out the beta and the omega. So again, taking the partial with respect to z of the sine function, we get cosine. Taking the partial with respect to z of the argument, we get minus beta. And here, taking the partial with respect to time of sine, we get the cosine. Differentiating the argument here, we get omega. So let's divide both sides by cosine of omega t minus beta z, and we get this condition right here, which is the condition for this being the solution of our wave equation. Solving for beta, we see that beta is equal to omega, the square root of the product of the permeability and the permittivity of the material in which our wave is propagating, and that's the condition for which this is a valid solution of Maxwell's equations. The reason we're interested in this uniform plane wave solution to Maxwell's equations is that we know whatever waveform we have, such as, say, a burst from a radar system, we can form that by a summation of cosine functions. So here is a plot of our electric field intensity at two different times, T2 and T1, where T2 is greater than T1. We know that when this argument of our cosine function is an integer multiple of 2 pi radians, the cosine is 1, and we're sitting at a peak of our waveform. Let's pick one particular peak. We do that by picking one particular integer. So let's set n is equal to 1, so that omega t minus beta z is equal to 2 pi radians. So this solid curve is our plot at time t1 of our electric field intensity. The dashed line is at another time t2, where t2 is greater than t1. As the time goes up, in order for omega t minus beta z to equal 2 pi, z must also increase. So that means this peak has moved to a larger value of z, so your waveform is propagating in the plus z direction. So let's differentiate this expression with respect to time. So the derivative with respect to time of omega t is just omega. Of the second term here, we'll get a dz dt. 2 pi is a constant, so the right-hand side is 0. So we can solve for dz dt, which is the velocity of our wave. So our plane wave is moving with velocity omega over beta. And our uniform plane wave is moving in the plus z direction. To write the equation for a wave moving in the minus z direction, what we do is we change this minus sign to a plus. So now for this argument of the cosine to remain a constant, such as staying on a crest of the wave, as time goes up, z must go down, indicating a movement in the minus z direction. So the velocity of a wave is omega over beta. But we also saw we had a condition placed on that uniform plane wave solution, and that condition was that beta is equal to omega times the square root of mu epsilon. So solving for omega over beta to get our velocity, we see the velocity of our uniform plane wave is 1 over the square root of mu epsilon. With this electric field intensity, there will be coupled to it a magnetic field intensity, and you can see that by looking at Ampere's circuital law. The changing electric field intensity will result in a magnetic field intensity. So let's find that magnetic field intensity. So let's go and look at Faraday's law. Here is the form of the curl in Cartesian coordinates, and our electric field intensity only has an x component. Expanding this determinant, we see there is no x or z component of the magnetic field intensity. There will only be a y component. So it will be transverse to our electric field intensity. Performing this differentiation, we get this term, which we can now integrate to solve for our magnetic field intensity. Replacing beta with the condition we have for our uniform plane wave from solving Maxwell's equations, we get the final form for our magnetic field intensity. So we've looked at Maxwell's equations and show that they predict a transverse electromagnetic wave whose velocity is given by 1 over the square root of mu epsilon. If we take the ratio of the magnitude of the electric field intensity to the magnitude of our magnetic field intensity, we see the result is the square root of mu over epsilon. This is referred to as the intrinsic impedance. Let's determine the velocity of our transverse electromagnetic wave in free space. So we know the velocity is 1 over the square root of mu epsilon, so let's put in the permeability and permittivity of free space. Here is our permeability of free space. Here our permittivity of free space. So we have this right here, which becomes 3 times 10 to the 8th meters over the square root of farad henries. A farad is a coulomb per volt. A henry is a Weber per amp. A Weber is a volt second. So the volts cancel. So we have coulomb seconds over an amp. And an amp is a coulomb per second. So we get seconds. When Clerk Maxwell made this calculation, he was the first person to realize that light is an electromagnetic wave. The speed of light in free space is given the symbol c, which comes from the Latin word celeritas, which means swiftness. These results were very controversial. Just the fact that you had an entity like an electromagnetic wave, the fact that it was moving with such great speed, the fact that that speed was the same as the speed of light, which implied light was an electromagnetic wave. And finally, that you could determine the speed from the permeability and permittivity of the material. The permittivity of free space comes from the DC measurement of forces between two charges, and the permeability of free space comes from the forces between two wires carrying a DC current. It seemed absurd that two quantities that came from DC measurements could give you the speed of light 3 times 10 to the 8th meters per second. Unfortunately, it was long after Maxwell's death before Heinrich Hertz verified the existence of electromagnetic waves. Let's calculate the intrinsic impedance of free space. I've substituted the permeability of free space and the permittivity of free space, which results in 377 square root of henries over farads. So we can see that a Henry over a farad is just an ohm squared. So the intrinsic impedance of free space is 377 ohms. Here we're looking at the electromagnetic spectrum. So along the left here we have the wavelength of our electromagnetic wave. On the right here we have the frequency as obtained from the frequency times the wavelength is equal to the speed of light. So starting at the shortest wavelengths, we go from gamma rays to X-rays to ultraviolet. This little sliver here is visible light. Then we move into the infrared and finally the radio and TV wavelengths. In the items of interest folder, I'm going to put up two videos, one on Young's double slit experiment and another one on the photoelectric effect and the wave-particle duality of electromagnetic waves.